All righty, we're back here. And what we're looking at here would be the next page in the notes. So now we're going to talk about a solenoid, which is just Slinky's magnetic cousin. So solenoid is just a wire that is wrapped in a coil. And so here they're talking about the current going in, and it would wrap around the coil and spiral and come out over here. So what that does, though, is that creates a wicked strong magnetic field in the center of this tube. And so the thought process here is if you have something like this and basically cut it open, kind of cut it right down the middle there and look down, what they're saying here is that we'd be looking sort of down into this. And so the current would be going in over here and coming around and coming out over here. And then it would spiral and go in here and come out there. And what happens here then is that if you put your thumb in the direction of this current going into the page, your fingers wrap in this direction. And so what that does is that contributes a magnetic field down the center of the tube going this way. Similarly, if you come over here and point your thumb in the direction of the current coming out of the page, your hand curls this way, again, creating a really strong magnetic field going down the center. So that's why the magnetic field is super strong down the center of a solenoid. Let's talk about how they get there, though, with an equation. So first of all, the magnetic fields almost cancel out on the outside. Pretty much they do. So a perfect solenoid is one in which there's no magnetic field outside the solenoid, and it's just super strong inside. And so if we look at what's going on here, they're going to say, all right, let's create an Imperial loop that goes from A to B, from B to C, C to D, and then back from D to A. So using Ampere's law, we can say mu naught I inc equals closed integral B dot ds. And we can do that again and talk about each of these paths as we travel, A to B, B to C, C to D, and back D to A. So if we go A to B, integral B dot ds, B to C, C to D, D to A, we can say, okay, going from A to B, looking at this B dot ds, this path here from A to B is just length h. And the dot product between, which is what we're talking about here, it'd be bs cosine theta. And here the B field and our path S happen to perfectly be aligned. And so that's why it would actually be bs, but S is h, so that's why we have bh. And if we look at B and C, this portion has zero contribution. And the reason for that is because the dot product for what's happening here with the B field being perpendicular to this path is zero, because cosine of 90 is zero. And so that's why this portion is zero. When we're here, there's not supposed to be any magnetic field outside. So even though we could have something that's parallel, or in this case, anti-parallel to the magnetic field, there's no magnetic field out here. So this portion is zero for that reason. And then the part that goes from D to A is zero because, again, cosine 90 is zero. So this is how all those set up, and this is why. So again, cosine 90 is zero. Here there's no B field. Here, cosine 90 is zero. So the whole equation comes down to mu naught I enclosed equals BH. Now, the solenoid is made up of a lot of coils, so it matters how many I's you have. So capital N being number of turns, we could put that in and say, all right, if we got 10 wires, it's better than having 5, and so that number matters. So that's why this capital N here is a multiplier. And in physics, little n typically means a number per something. And so little n would just be the number of turns we would have total divided by the length that we have to make those turns. So another way to say little n would be to say big N divided by little n would be the big N divided by the length that we have to make those coils. The length that we have in which to place those coils. So that would be little n, and so little n times h is what gives us big N. So that's the same equation here, and basically we can cut it out and just drop it to this. And this is the equation for magnetic field in a solenoid. And that's for an ideal solenoid. That's probably a good spot to stop right there.